SwayamPrabha. Digital India. Educated India.
Welcome to today class of nonlinear vibration. So, this is the third lecture in the second module of this nonlinear vibration course. So, last two classes we have studied how to derive this equation of motion using this Newton's second law or D'Alembert principle for this discrete and distributed mass system. Also, last class just I have started how to use this Lagrange principle to derive the equation of motion. So, today class we will solve some more examples to solve or to find the equation of motion by using this Lagrange principle. Also, we will use this extended Hamilton principle to derive some equation of motion. So, yesterday or last class we have studied about this Euler-Bernoulli beam equation. So, we have derived this beam equation using this Newton's second law. So, by drawing the free body diagrams we have written the equation of motion or we have found the equation of motion. So, this is the equation of motion of a Euler-Bernoulli beam equation. So, similarly we have taken another example where we have taken a slender beam subjected to base motion and we have derived this equation of motion. So, which is a spatio-temporal equation of motion. So, in case of spatio-temporal equation of motion, that is the VST, that is the transverse displacement of the beam can be written as by considering number of modes. So, you can write this equal to psi I x and q I t. So, it is a function of both displacement and time, unlike in case of lumped parameter system where the displacement is a function of time only. So, here the displacement is a function of both space and time, here the displacement is a function of both space and time. So, last class we have derived this equation of motion, first the spatio-temporal equation of motion by using this D'Alembert principle, where we have taken this ms equal to ei into ks and that ks equal to phi dash and this is phi, this is the angle, and by writing this sin phi in terms of this v and or v dash. So, we have derived this nonlinear equation of motion. So, the nonlinear equation of motion, after deriving the spatio-temporal equation of motion, then we have used generalized Galerkin principle. So, either one can use this multi-mode generalized Galerkin principle or single mode Galerkin principle where this n equal to only 1. So, if you take n equal to only 1, then it will reduce to r psi n s into u n t. So, or n will be equal to 1. So, in that case it will be r psi into u. So, in that case by substituting that equation, so you will get a equation in its temporal form. By substituting this equation in the spatio-temporal equation and so as this is this shape function may not be the exact eigenfunction. So, there will be some residue. Now, by minimizing this residue one can get this temporal equation of motion. So, in this way one can get the equation of motion. So, then in Lagrange based approach, so last class we know what is the Lagrange equation. So, this is equal to d by dt of del t by del q k dot minus del t by del q k equal to capital Q k. So, here q k is the generalized coordinates. So, we have discussed regarding the generalized coordinate. For example, in case of this simple pendulum, the example of simple pendulum was given. So, here the position of the bob can be written by its coordinate x and y. So, this is the physical coordinate So, but these physical coordinate x and y are interrelated by the constant equation, that is x square plus y square equal to L square, x square plus y square equal to L square. But instead of using these two coordinate x y, one can use this coordinate, that is theta, to express the position of the mass. So, here x will be equal to, so you can write what is x. So, x equal to L sin theta and y equal to L cos theta. So, that way one can write this coordinate or the position of the mass by using this generalized coordinate theta. So, generalized coordinate is nothing but the minimum number of coordinates required to express the motion of a body. Here by using only theta, so we can express the motion of the mass. So, now you know now the generalized coordinate. So, here q k as q or k equal to 1, here k equal to 1 only single degree of freedom system. So, q equal to 1. So, this q 1 equal to theta. By using q 1 equal to theta, we can derive this equation of motion. So, here T is the kinetic energy of the system and and q 1 dot or q k dot is the velocity term. So, differentiation of q k is q k dot. So, d by dt of del t by del q k dot minus del t by del q k equal to capital Q k. So, here by taking this t minus u equal to L, that is the Lagrangian of the system. So, this equation can also be written by d by dt of del L by del q k dot minus del L by del q k equal to capital Q k. So, this is the generalized force. So, the generalized force can be written by using this expression. If only force is there, then the first term only can be written. If both force and moment are acting on the system, then this moment term also can be written. So, capital Q k, that Q k equal to summation f I dot del r I by del Q k. What is r I? R I is the position vector. So, in this case the position vector of this mass, that thing can be written by using the r I. So, r I in this case it will be equal to, so x I plus y j. So, by using the coordinate system I and or the unit vector along x direction as I and y direction as j. So, in a vector form r can be written as x I plus y j, and in that way also force can be, if some force is acting on the system, then that force also can be written in a vector form. Then by doing the dot product, we can find this generalized force. Similarly, from the moment side also m I dot del omega I by del q k will give you the q k. So, let us take this example, one simple example of the simple pendulum. So, here the velocity. So, for finding the kinetic energy, we know we must have to find the velocity. So, one has to first write down the position vector r. So, or let this length equal to L. So, if the length equal to L, then so one can write the velocity equal to L theta dot or L omega. So, then kinetic energy equal to half m into L theta dot square. Similarly, potential energy. So, potential energy is due to change in this position. So, initially the mass was here, so at a length L. So, now as it has moved to this position, so this is the change in position. So, this u equal to, so u will be equal to mgl into 1 minus cos theta. So, this angle is theta. So, this angle is theta. So, this is L cos theta. So, total length equal to L. So, this is L cos theta after moving an angle theta. So, the change in height equal to L into 1 minus cos theta. So, change in potential energy, that is your u equal to mgl into 1 minus cos theta. So, now taking t equal to half m L theta dot square and u equal to mgl into 1 minus cos theta. So, we can derive this equation of motion. So, the equation of motion can be derived similarly for a double pendulum. So, you can write this first, you can write this position vector r1 of this, and then so this is position vector of the first mass. Similarly, the position vector of the second mass you can write. So, after writing the position vector of first mass and second mass, by differentiating that thing you can write down the velocity term. Then after getting the velocity term, then the kinetic energy term can be written and potential energy can be written. So, as this energy term are scalar term, so you need not have to worry much regarding the direction. So, after finding this velocity term and the kinetic energy and potential energy, then by writing L equal to T minus U, L equal to T minus U, and then using the Lagrange principle d by dt of del L by del q k dot minus del L by del q k. So, equal to, as no force is acting, then you can put it equal to 0 and you can derive this equation of motion. So, the equation of motion can be written in this matrix form like this. So, here it has been taken that the sin theta 1. So, this is theta 1. So, sin theta 1 and theta 2 are small. So, if theta 1 and theta 2 are not small, then it will be replaced by sin theta 1 and sin theta 2 term. So, this way one can derive this equation of motion by using Lagrange principle. So, for example, let us take another example. So, here this is a 2 degrees of freedom system. So, initially the mass, this cart is at this position, this dotted position. Now, it has shifted to this position. So, in this cart, so there is a pendulum, compound pendulum or a rod hanging from this cart. So, when this is moving, when the cart is moving towards right, the pendulum, this compound pendulum or the bar is rotating by an angle theta. So, initially you must write to solve this type of problem. So, first you write the position by using this position vector. So, here we have fixed the coordinate system, physical coordinate system about this axis. So, about the y axis we have fixed the coordinate system. So, we can write the position vector. So, after writing the position vector, then we can write down the velocity term. So, after writing velocity, we can find the kinetic energy and potential energy, and then we can find the equation of motion. So, for example, in this case, let us assume that the mass, this cart has moved by an amount x. Initially, it was at this position, the center of this point was here. So, at a distance r0 and it has a displacement of x. So, when it is moving by an amount x, let the bar hanging from this position. So, it has rotated by an amount theta. So, the position, so we can write down the position vector of this point C, let this point is C, then the position vector r c will be equal to r0 plus x plus this distance. So, let us take that of the center of mass is C. So, we have taken the center of mass as C. So, let the center of mass is at L by 2 distance from this thing. So, this is L by 2 into, so this distance equal to sin theta. So, L by 2 sin theta. So, this angle we have taken theta. So, this is L by 2 sin theta. So, R c equal to R 0 plus x plus L by 2 sin theta. So, we have taken this direction I and along the vertical direction as j. So, minus, so this is the horizontal component and vertical component will be equal to minus L by 2 cos theta. Vertical component, this is the vertical component, and it is in downward direction. So, that is why this negative sign. So, minus, so we can have this minus minus L by 2 cos theta 2. So, the kinetic energy, now this velocity differentiating this term. So, the velocity equal to r 0. So, differentiation of r 0 equal to 0. So, differentiation of x equal to x dot, then this L by 2 sin theta will give you half L by 2 cos theta into theta dot I plus then this cos term cos theta term. So, this part differentiation gives L by 2 theta dot sin theta j. Then this kinetic energy is due to this mass translation of the mass. So, that is equal to half m x dot square, and for this rod also. So, kinetic energy of this rod. So, the center of mass. So, two way you can find the kinetic energy of this rod, either pure rotation about this point, let me write this point as O, pure rotation about O you can write, or both rotation and translation about point C, that is the center of mass. So, by writing about C, so you can write this is equal to half m v c dot v c, that is velocity dot velocity. So, you know that is equal to half m v square plus then half I c into theta dot square. So, you can write this by expanding this thing, then you can write this is equal to half m plus m x dot square plus m l x dot theta dot cos theta plus 1/3 m l square theta dot square. So, here actually by without solving this equation or expanding this equation by hand manually, you can use symbolic software like this Mathematica or Maple, or you can write the equation or write this thing in MATLAB also in symbolic form to differentiate. First you write down your RC, that is position vector, then differentiate to get velocity, then write the expression this way in symbolic form so as to get this equation of the kinetic energy. So, when the expressions are very big, so it will be difficult to write down or find the equations by manually doing this problem. So, in that case you must have to use this mathematical software or symbolic software to derive this equation of motion. So, now you know how to find this kinetic energy. Here you just see either. So, if you will take actually rotation about O, so that will be equal to 1/3 m l square theta dot square. So, you can see a couple term here, so which contain both x dot and theta dot. So, this term contain both x dot and theta dot. So, here you have a term x dot square. So, here you have a term theta dot square. So, completely this is a 2 degrees of freedom system. So, with x as 1 degree of freedom and then this theta is another degree of freedom. So, now potential energy. So, we have a spring here. So, as the spring is having a displacement. So, initial. So, spring is having a displacement of x. So, let us write or take the take the stiffness of the spring as k. So, in that case it will be half k x square, and as the mass position of mass is changing by L by 2 1 minus cos theta, then the potential energy of the system equal to V equal to half k x square plus mg L by 2 into 1 minus cos theta. So, now by writing this L equal to T minus V. So, T minus V. So, half m plus m x dot square plus m l x dot theta dot cos theta plus 1/3 m l square theta dot square minus half k x square plus mg L by 2 1 minus cos theta. You can use this Lagrange principle d by dt. You just see you have two coordinates. So, this is 2 degree of freedom system. So, here you have q1, you can take q1 equal to x and q2 equal to theta. So, as q1 equal to x and q2 equal to theta. So, two equations you can find. So, d by dt of del L by del q k dot, that is del x. So, first you can do with respect to this, then del L minus del L by del x. So, this will be equal to. So, you just see. So, if there is no force, then it will be equal to 0. So, if some forces are acting, then it will be generalized coordinate capital Q1. Similarly, your second equation will be d by dt of del L by del theta dot minus del L by del theta. So, this is equal to 0. So, by using these two formulas, so you can derive this equation of motion. So, this way you can use this Lagrange principle to derive this equation of motion. So, here there is a force acting. So, if there is a force acting, then that forcing will be there. So, let us see if there is a force. So, here a force F is acting. So, as F is acting, so you can find, so how to find this Q? So, Q is nothing but, so here in this case you can have Q1 and Q2. So, you know the formula Qk equal to summation I equal to 1 to n. So, in this case you can have 2. So, this will be equal to Fi dot del Ri by del Fi. So, this is del Ri by del Qk. So, this capital Qk equal to Fi dot del Ri by del Qk. So, here assuming the force acting in this horizontal direction, and also you have a mass also acting mg downward is also acting. So, taking both the forces, so you can derive, you can find the equation of motion. So, already you have found this Ri, and then by using that thing, so you can find this equation. So, in the first case your Q1 becomes F, and in the second, so Q2 becomes Fl cos theta. So, you have this is the equation of motion. So, you got. So, you just see, so this is not a equation of motion of a linear system. So, in this case the equation of motion, so you can further expand. So, the sin theta and cos theta term, here also you have a combination of x dot and theta dot term. So, by expanding the sin theta, cos theta and taking note or making them of higher order. So, you can get this nonlinear equation of motion. So, this way you can find the equation of motion by using Lagrange principle. So, let us see if we want to use this extended Hamilton principle, then how we can derive this equation of motion. So, to derive this extended Hamilton principle, actually you must know this principle and how this principle works. So, in case of the extended Hamilton principle, the assumption is that, so let this is state 1, this is state 2. So, let the body is moving from state 1 to state 2. So, let this is your state 1, this is state 2. So, you can have a, so let this is the reference coordinate system. So, from the reference coordinate system, so this is, you can take the position vector at any time. So, you can take that position vector, you can find, and so there are several paths from 1 to 2. So, one can follow several path, let for this is 1, let this is another path also. So, out of many path, so this is another path also. So, out of many path, one path will be the true path and other paths will be the varied path. So, if this is the true path, let it is equal to, you can write this position Ri, and the position vector of any of the varied path can be written by using, so this is delta Ri. So, it will be Ri plus delta Ri, the position vector. So, this is O. So, you can take this x, y, z, x, y, z. So, coordinate systems you can take and you can find the position vector. So, let the, so it is moving from position 1 to 2. So, the assumption is that, so in this extended Hamilton principle, the assumption is that the varied path and the true path intersect at this point 1 and 2. So, it meets at point 1 and 2. That means, this delta Ri at T1, T equal to T1, or at T1 and T2, you can tell that way also. So, at T1, T2, so that is equal to 0, delta Ri at T1 equal to, so at this position, position 1, so that is position 1 equal to 0, and delta Ri at T2 also equal to 0. So, this is the basic assumption in this extended Hamilton principle. So, taking or knowing this varied path and the actual path. So, this extended Hamilton principle is derived. So, that principle is del t minus u plus delta w n c dt equal to 0, and already I told you the condition. So, this is delta r 1 at t 1 equal to delta r I at t 2 equal to 0. So, here T is again the kinetic energy and U is the potential energy, and WNC is the non-conservative work done. So, WNC is the work done due to non-conservative forces, work done due to non-conservative force. Okay, so already you know, so there are two type of force, one is conservative force and second one is the non-conservative force. In case of the conservative force, the work done in a cycle, so let it start from here and come back to this position. So, the work done equal to 0, and in non-conservative force, as there will be some loss of energy. So, this will not be equal to 0. So, for example, work done due to friction and where the losses occur. So, there the work done is known to be that due to non-conservative force. So, writing this L equal to T minus U, one can write down this equation in this form also, delta L plus. So, delta is the delta, this is the delta operator, differential operator. So, integration T 1 to T 2 delta L plus delta W N C dt equal to 0. So, this is the extended Hamilton principle. So, here, so R I is written in terms of the physical coordinate system. So, you know already the physical coordinate system, R I is the physical coordinate and Q I is the generalized coordinate. So, Q, so these are the generalized coordinate. Okay. So, by using this generalized coordinate q y, so you can derive the, or you can write down this equation of motion, or you can find the equation of motion. So, if there is no conservative force, there is no conservative force, that is delta w, no non-conservative force, that is delta w n c equal to 0, then this equation reduces to this, that is integration T 1 to T 2 delta L dt equal to 0, q k at T 1 equal to q k at T 2 equal to 0. So, this equation is known as Hamilton's. So, this is from the, so this is your Hamilton's principle, and this is extended Hamilton principle. So, the extended Hamilton principle is for by extending or including this non-conservative work done due to non-conservative force. So, when this non-conservative force equal to 0, so this extended Hamilton principle reduces to Hamilton's principle. So, according to your Hamilton's principle, so integral T 1 to T 2 delta L dt equal to 0. So, let us see with some example. So, we can see this thing. We can take the example of the simple pendulum. Same example of simple pendulum and derive this equation of motion by using this Hamilton principle. So, already we have seen that velocity if this angle is theta, if this length is L. So, this velocity equal to L theta dot. So, this kinetic energy T equal to half m L theta dot square, and U potential energy equal to mgl into 1 minus cos theta. So, L equal to T minus U equal to half m L theta dot square minus mg L into 1 minus cos theta. So, now let us derive this thing. So, this delta L dt equal to 0. So, according to this principle delta theta, so here q k equal to q k equal to 1. So, and q equal to theta, that is the generalized coordinate q equal to theta. So, theta at t 1 equal to theta at t 2 equal to 0. So, let us integrate this thing. So, by now we have to apply this del operator. So, del of half m L theta dot square minus m g L into 1 minus cos theta. So, you just see this will be integrated dt delta L dt. So, here non-conservative work done delta W N C equal to 0. So, we are not, there is no force acting on the system. So, you can take it is equal to 0. So, and you can make it equal to 0. So, now if this delta operator can enter inside this thing, so you can write or by slightly expanding this thing. So, this integral t 1 to t 2. So, this becomes integral t 1 to t 2, then delta of half m L theta dot square minus m g L into 1 minus cos theta dt equal to 0, or this is equal to t 1 to t 2 half. So, this thing now this operate this del operator here. So, by putting this del operator here, this constant half m is also constant. So, L theta dot square. So, this becomes 2 into, you just see this is, so this is 2 into, you can see this part. So, 2 into L theta dot. So, this is L theta dot, then del of L theta dot you have to write. So, from del of L theta dot, this L has come constant taken out, then this becomes theta delta theta dot. So, now this part by putting this del operator, so this becomes half m into 2 L. So, this 2 has come here. So, this 2 has come 2 into L theta dot, then del. So, actually you can write this way. So, del of half m L theta dot square equal to half m del of L theta dot square. So, this is equal to half m 2 into L theta dot into del of L theta dot. So, this becomes half. So, this 2 and half cancel. So, this has gone. So, this becomes m L, this is theta dot. Then from this thing, so we can write this is equal to another L will, this L is constant. So, m L square theta dot into del theta dot. So, here is the trick you have to play. So, this part by expanding, so you can write this thing in this form m L square theta dot. So, this del theta dot you have to write this way, del of, so theta dot is nothing but d theta by dt. So, you can exchange these things and you can write this equal to m L square theta dot into d by dt of del theta. So, this is the trick actually you have to play, so that you can derive this equation easily. So, this part you just see it is written this way. So, m L square theta dot d by dt of del theta, d by dt of del theta. So, here delta theta dot is written in this form. So, you have to remember this part only while deriving the equation motion. So, delta theta dot equal to del of d theta by dt. So, this d theta by dt is taken out. So, that this becomes m L square theta dot d by dt of delta theta. So, this is only the tricky part of this derivation, otherwise you can follow the standard procedure of differentiation and integration and you can have it. So, then this part is minus mgl. So, from the potential energy differentiating this thing. So, mgl del of mgl equal to 0. So, then minus minus plus. So, this becomes mgl cos theta. So, del of mgl cos theta. So, that gives rise to minus mgl sin theta and delta theta. So, dt. So, now you can easily integrate this thing. So, this m L square theta dot d by dt of delta theta into dt. So, dt will cancel. So, this integration becomes m L square theta dot d of d theta. So, now you can integrate is easily by applying this integration by parts. So, this becomes, so you have the integration. So, you just see the integration was m L square theta dot into del theta. So, you have to integrate. So, this was, let us see this again. So, this is m L square theta dot d by dt of delta theta into dt. So, this is written d by, so you just see this part. So, this is d by dt of delta theta into dt. So, this integration you have to do. So, let us take this as the first part and this as the second part and do this integration by parts. So, this integration is from T1 to T2. So, first part remain as it is. So, you can put it m L square theta dot and integration of d by dt of del theta dt. So, this becomes integration of this differentiation part, this becomes delta theta. So, this from T1 to T2, then minus integration T1 to T2. So, this is integration by parts. So, this delta theta remain as it is, then differentiation of this part. So, differentiation of this m L square theta dot. So, differentiation of m L square theta dot is nothing but m L square theta double dot. So, this becomes m L square theta double dot d square theta by dt square. So, the first term you got in this integration, this is m L square theta double dot into this delta theta is taken outside into delta theta into dt. Then from the potential energy, so the from potential energy term, so you have another term. So, this term equal to minus mgl sin theta delta theta dt. So, integration of this thing, so this is sin theta delta theta dt. So, that integration becomes, so you just keep it as it is. So, you need not have to expand that thing. So, just you have to keep it is as it is. So, this becomes mgl sin theta delta theta dt. So, now you just see already we know our delta theta or delta Ri at T1 equal to delta theta at T2 equal to 0. So, already we know this thing. So, this part tends to 0. So, this part as delta theta at T1 equal to delta theta at T2 equal to 0. So, this part becomes 0 and this is the part as delta theta is arbitrary, delta theta is arbitrary. So, it cannot be 0. So, the integral to be 0. So, we must have this part equal to 0. So, this part is nothing but the equation of motion of the system. So, from this thing, so you can find, so this m L square. So, this way we can find the equation of motion of the system. So, now expanding the sin theta. So, we can write this sin theta equal to theta minus theta q by 6 plus theta fifth by 120. So, the equation of motion becomes theta double dot plus g by L theta minus theta q by 6 plus theta fifth by 120 equal to 0. So, this way you can apply this extended Hamilton principle to derive this equation of motion. So, let us take one more example. So, previous thing we have taken a discrete system. So, let us take one more example where we have a continuous system and so let a force Pt is acting axial in axial direction. So, we have a cantilever beam subjected to a axial force Pt and for the system. So, we want to derive this equation of motion. So, here let us take this m equal to mass per unit length, then m. So, by taking a small element dx at a distance x, we can take a small element dx. So, mass of the small element becomes m into dx and the kinetic energy of the systems will be equal to, for the small mass first you find, that is delta t. So, delta t will be equal to half m. So, let the transverse displacement can be written as w, then this differentiation d W by dt can be written, but here instead of write d, so you can put the del W by del t, because W is a function of both space and time. Okay. So, W by del W by del t, so that is velocity, or it is written as W comma t. So, this is velocity square. So, half mv square. So, this is velocity, del W by del t is velocity. So, this delta t, that is kinetic energy of the small element, can be written as half m del W by del t square. So, total kinetic energy will be integral of that thing, integration 0 to L m W t square dx, and then potential energy. So, strain energy already you know, so strain energy can be written in this form. So, half integration 0 to L E I del square W by del x square whole square. So, this is the potential energy or strain energy of the system, and T is the kinetic energy. So, you can write L equal to T minus U equal to half 0 to L m W t square dx minus half 0 to L E I W square. So, double differentiation of W whole square dx. So, now by taking this inextensibility condition, so we can take, so for example, this is a small element if you take. So, in the small element, let the displacement along x direction equal to u, and in the y direction or in this transverse direction it is w. So, you can find, so this inextensibility conditions by using this expression. So, that is 1 plus del u by del x whole square plus del w by del x whole square equal to 1, or from this thing. So, you can get u, that is the displacement in this form. So, u equal to minus half integration 0 to L dw by dx square dx. So, this way you can write, or you can use this partial derivative also. So, if you are considering w is a function of x and t, otherwise if you are considering for the time being w is a function of t. So, this way also you can write. So, you got u, that is the deflection or displacement in x direction. So, you have to find the work done due to non-conservative force, that is due to this force P t, the work done. So, delta WNC will be equal to minus P delta U. So, that is equal to, as we are putting this compressive force and assuming that U is taking place towards right, then you can put this minus delta U, work done equal to minus P into delta U. So, that is equal to half P into, for U you can substitute this expression. So, that you can get half P delta 0 to L W dash square. So, this is W dash square dx. So, now by knowing this L and WNC delta WNC, so we can easily derive the equation of motion. So, the equation of motion can be easily derived by using that expression. So, now by applying this extended Hamilton principle, so that is integral T1 to T2 delta L plus WNC or delta L plus delta WNC dt equal to 0, and condition is that delta W at T1 equal to delta W at T2 equal to 0. So, we can find the equation of motion. So, here, so this now by expanding this term, so L equal to T minus U, already we have written this is L and this is from P. So, now just you have to expand this thing by integration by parts. So, here m delta, so this part actually you have to expand and other part just you have to take as it is. So, this is delta of del W by del T square. So, this part you have to just expand. So, this will be equal to half into 2 into m into delta of del W by del T. So, this thing already I have explained. So, this will be equal to m, this is del W. So, you can exchange this thing. So, by exchanging this, so it will be m d by dt of delta W. So, if you can write this half m delta del w by del t square in this form, and then by using this integration by parts. So, easily you can derive this equation of motion. So, you just see this term now it can be written in this form. So, integration T1 to T2 integration 0 to L m into del w by del t del of del w by del t dx dt minus integration T1 to T2 integration 0 to L E I del square w by del x square del of del square w by del x square minus p into del w by del x del of del x by del w by del x dx dt. So, you just see now this part you have to integrate by parts. So, if you integrate by parts, then this equation of motion can be obtained easily. So, you can obtain the equation of motion easily, and you just see. So, this is the equation of motion. Now, you just see this part. So, when you are integrating it by part, so this becomes m del w by del t into del w. So, this is T1 to T2. So, you know del w T1 equal to del w T2 equal to 0. So, this part actually will be 0 as per the definition, and so this part is the boundary conditions. So, this is integral T1 to T2 E I del square w by del x square del of del w by del x 0 to L. So, either this part will be equal to 0, that is del square w by del x square, that is bending moment, or this del w by del x. So, del w by del x is nothing but the slope, or this part you can see. So, this is the shear force, this component is the shear force, and or this del w. So, here del w is nothing but that is the displacement. So, either the slope will be 0, or so 4 different boundary conditions are generally there in case of the beam. So, those 4 different boundary conditions are displacement, either displacement will be 0, slope will be 0, bending moment will be 0, or the shear force will be 0. So, in this case, so this is the boundary conditions you have got, and this part you just see this part which is coefficient of delta w dx dt. So, as delta w is arbitrary, so this is the equation of motion of the system. So, the equation of motion of the system becomes m del square w by del t square plus E I del fourth w by del x fourth plus p del square w by del x square. So, if one will take this p, so one can take this p equal to, so as I have told Pt I have written there. So, you can take this T P Pt equal to, by taking Pt equal to P0 plus P1 cos omega t you can take also. So, this is equal to P0 plus P1 cos omega t. So, by taking this, so you can have a nonlinear equation of motion. So, which will be that of a parametrically excited system. So, with this, so today class will conclude here. So, this way you can derive this equation of motion of any system, any physical system, by using either this Newton second law or D'Alembert principle, or by using this Lagrange principle or this Hamilton principle. So, these equations actually we have derived when you have a fixed coordinate system. So, if the coordinate systems are not fixed, so that time, so you have to use either this Lagrange Euler formulation or this Newton Euler formulation. So, we will study or we will take some examples of Lagrange Euler formulation or Newton Euler formulation during project phase of this course. And also, so you have to derive this equation motion by using the symbolic software like Mathematica or by Maple or some software like this MATLAB also. In MATLAB also you can derive this equation of motion. First you write down the position vector, then differentiate that thing to find this velocity, then write down the kinetic energy, then write down this potential energy, then either apply Lagrange principle or Hamilton principle and derive this equation of motion. So, these things will be given you as assignment in this course to derive this equation of motion for a number of systems using symbolic software. So, thank you. So, this is the end of this module, second module. So, next class we will study the third module. Thank you very much.